What if I told you the fundamental rules of the universe completely change the second you look away? I know, it sounds totally bizarre, but that is the astonishing reality of the microscopic world. Down at the subatomic scale, nature is playing by a completely different rulebook, one that basically shatters everything we think we know about reality itself. Welcome to this explainer. I am so pumped to be diving into this with you today because we are tackling what is hands down one of the most mind-bending, fascinating topics in all of science: quantum mechanics. We're going to demystify the atomic and subatomic world together, and trust me, it's going to be a wild ride. If quantum physics feels a little intimidating, don't worry at all. We're going to break this down into totally manageable pieces. Here's our roadmap. First, we'll go beyond classical physics. Then we'll dive right into the weird quantum rules. After that, we'll try interpreting the impossible, check out quantum tech around us, and finally, we'll peer into the final frontier. Let's get right into it. Section 1, Beyond Classical Physics. To really understand where we're headed, we first need to look at the limits of what we thought we knew. Think about the ordinary world we see and touch every day. That's governed by classical mechanics. It deals with continuous values and deterministic predictions. Basically, if you know the exact starting conditions of a classic system, you can predict exactly what's going to happen. But when we zoom way, way down to the submicroscopic scale of atoms and subatomic particles, classical physics just falls apart, completely fails. That is where quantum mechanics takes over. Instead of smooth, continuous values, things like energy and momentum are boxed up into tiny, discrete packets. And here is the real kicker. Instead of absolute certainties, quantum mechanics runs entirely on probabilistic predictions. We literally cannot know for certain what a particle will do. We can only calculate the odds of what it might do. Now, a massive paradigm shift like this didn't just happen overnight. It was a gradual unraveling of the old rules. It really kicked off back in 1900 when Max Planck was trying to solve a puzzle with black body radiation. He proposed that energy isn't continuous, but radiates in these little discrete packets he called quanta. And get this, he actually just thought of it as a neat mathematical trick. But then, in 1905, Albert Einstein came along and took it literally to explain the photoelectric effect, showing that light itself has a particle nature. These early ideas sort of simmered as the old quantum theory until the mid-1920s, when heavyweight physicists like Werner Heisenberg, Erwin Schrödinger, and Max Born hammered out the full mathematical formalisms that we still use today. All right, Section 2, the weird quantum rules. We've left the familiar macroscopic world in the rearview mirror, so it's time to explore the truly bizarre phenomena that run the atomic universe. Let's start with a foundational and frankly mind-blowing concept: superposition. In our everyday reality, a coin resting on a table is either heads or tails, right? It's one or the other. But down in the quantum world, before a measurement actually occurs, a quantum particle isn't in a single definite state. Instead, it exists as this sort of blurry combination of all its possible states at the exact same time. It's effectively both heads and tails, right up until the very millisecond an observer or a piece of equipment interacts with it. The Mach-Zehnder interferometer experiment shows off this mystery perfectly. Imagine we fire a single solitary photon of light into a beam splitter. Now, classical logic tells us it should either bounce one way or go straight. It has to pick a distinct path, right? But quantum mechanics says no. That photon enters a genuine superposition. It somehow incredibly takes the upper path and the lower path simultaneously. And we know this for a fact because when those paths are brought back together, they create an interference pattern, a pattern proving that the single photon literally interacted with itself. But here's the wildest part. If we try to block one path just to peek and see which way it really went, the interference pattern just vanishes. It only takes both paths when we aren't looking. And that brings us directly to wave-particle duality. Electrons, photons, even whole molecules pull this dual identity trick. They exhibit characteristics of both distinct little particles and spreading continuous waves. But here's the catch. Which one they are depends entirely on how they are measured. When you fire them through a double-slit experiment, they travel like a wave of probabilities, interacting with themselves to create bands of light and dark. But the second they actually hit the screen, boom. They always absorb at discrete specific points, just like solid little particles. They travel as waves, but they arrive as particles. All these strange behaviors lead to something even more incredible: quantum entanglement. Erwin Schrödinger actually called entanglement the characteristic trait of quantum mechanics. Basically, when quantum systems interact, their properties become mathematically tangled up together. You literally cannot describe one particle without describing the other, no matter how far apart they are separated in space. Now, a quick caveat here. While this mathematically links particles across vast distances instantaneously, physicists have proven you can't actually use this to send usable signals faster than the speed of light. Still, it absolutely proves that deep down, nature at this scale is profoundly, fundamentally connected. Which brings us to Section 3, Interpreting the Impossible. So we've got the math, and the math works flawlessly. But what does it actually say about the fundamental fabric of reality? If your brain is hurting a little bit right now, take a deep breath. Richard Feynman, one of the most brilliant Nobel Prize-winning physicists of the 20th century, famously said, "I think I can safely say that nobody understands quantum mechanics. The probabilistic nature of reality just completely defies human intuition. So if you're finding this all deeply strange, congratulations. You are in the exact same boat as the very founders of the field." So that leaves us with the biggest philosophical question in all of modern physics. How do we interpret a reality that is fundamentally built on probability? When a system is sitting there in a superposition of many states, and then is measured and collapses into just one single reality, what actually happened? What is the physical mechanism behind that collapse? Well, scientists have come up with some wildly different interpretations to try and explain this. The Copenhagen interpretation, championed by Niels Bohr, basically argues that this probabilistic nature isn't just a temporary gap in our knowledge, it's a final renunciation of classical causality. In this view, the actual act of measurement is what forces the wave function to collapse into a single state. Then you've got Hugh Everett's many worlds interpretation. This one just throws the idea of a collapse right out the window. It proposes that all possibilities actually happen simultaneously, and the universe is constantly branching off into mostly independent parallel multiverses. And finally, there's Bohmian mechanics, which argues that quantum mechanics is actually deterministic. It suggests particles really do have exact positions at all times, but they're being guided by hidden underlying forces we just can't see. There's still absolutely no consensus on which of these is correct, but each offers a totally stunning perspective on how the universe might operate. Moving on to Section 4, Quantum Tech Around Us. Let's snap back to tangible reality for a second. I know, all this talk of multiverses and probability waves sounds incredibly abstract, but it is actually aggressively practical. Modern technology operates at a scale where these weird quantum effects aren't just quirks, they are absolutely essential. Without our understanding of quantum mechanics, the everyday tech we rely on simply wouldn't exist. The stimulated emission of radiation, that gives us lasers. Understanding the tiny spin of particles, that gives us life-saving MRI machines in hospitals. The entire modern digital age is built on semiconductors, transistors, and microprocessors that rely entirely on quantum flow. And looking ahead, we are actively developing quantum computers that harness superposition and entanglement to solve problems classical computers never, ever could. To give you a super concrete example, imagine throwing a tennis ball at a thick brick wall. Classically, it bounces back. It obviously doesn't have the energy to smash through. But in quantum mechanics, because a particle's location is just a wave of probabilities, there is a tiny non-zero chance that the particle will simply appear on the other side of that solid barrier. It effectively tunnels right through the wall. It sounds like magic, but this impossible trick is exactly why the sun shines. It's what enables nuclear fusion in stars. It also allows for radioactive decay, and on a very practical, everyday level, it's the exact mechanism used to erase and write data in the flash drive sitting in your pocket right now. And that brings us to Section 5, the final frontier. We've seen how insanely powerful quantum mechanics is, but it has one glaring, frustrating flaw. It really doesn't play well with the rest of physics. We're currently dealing with an epic clash between our two best theories of the universe. On one hand, you have Albert Einstein's general relativity, which beautifully explains gravity, the cosmos, and everything on the macro scale. On the other hand, quantum mechanics flawlessly explains the subatomic forces at the micro scale. Both of these theories have been proven true by incredibly rigorous, repeated empirical evidence, but their abstract mathematical frameworks directly contradict each other. If you try to use the math of quantum mechanics to explain gravity, the equations just blow up and spit out impossible answers. They absolutely refuse to merge. Resolving this massive inconsistency is the ultimate goal of 21st century physics. Scientists are desperately hunting for an elegant theory of everything to unite these models, and right now there are two main contenders stepping into the ring. The first is string theory. This idea posits that point-like particles aren't actually points at all, but rather tiny, one-dimensional vibrating strings. The way they vibrate gives particles their specific properties, including the elusive force of gravity. The second major contender is loop quantum gravity. This theory attempts to quantize space itself, suggesting that space-time isn't smooth, but is actually woven out of extremely fine, finite loops called spin networks at the impossibly small Planck length. Both are just incredible, ambitious attempts to completely rewrite our understanding of reality. Which leaves us with this final, profound question to ponder. How does the quantum description of reality, with all its superpositions, probabilities, and entanglement, actually give rise to the solid, completely predictable reality that we see and touch every single day? The universe is following a set of invisible, magical-seeming rules right under our noses, and we are only just beginning to uncover the code. Thank you so much for joining me on this explainer. Keep wondering, keep questioning, and I really hope this leaves you eager to learn more about the universe's hidden microscopic rules.